Good morning all. Welcome to this GIAN program, second day. I will start with this lecture 11 and 12, microgrid system design and hybrid energy systems for microgrid. And after that I will present this lecture 13 and 14 separate slides, energy systems of energy management of microgrid system. So here microgrid system design, as I explained, you can call it microgrid or even the hybrid power system. So here I will discuss about this microgrid, start with the importance, general introduction. Then here in this mainly we focus microgrid, like say if the microgrid is like in the remote areas, okay, as we said that it can be connected with the grid or it can be isolated. So and we are covering several topics and some topics overlap, same issue we speak differently. So here like we talk about the particularly the isolated microgrid. If you are designing the isolated microgrid, so here in the isolated microgrid, what will be the different components for the microgrid that we are going to design. So this, as you see that what we can have the different components in the microgrid, it can depend upon what are the natural resources available. Accordingly we can have the microgrid. So there is one book very nicely written, little bit old, that very nicely talks about the design of wind diesel hybrid power system. So some part I have discussed from that book, and then of course I added some research conducted by me and my researchers as well. So here first talking about the, when we are talking about the like say remote locations, isolated microgrids, like still worldwide there are many locations where we do not have electrical connection to the central grid network. Okay, I give example. Even our country, not many, but still few locations could be there where we do not have the grid supply. And particularly I mentioned like in the African continent, there are so many locations, significant population still there where there is no grid supply. It can be due to several reasons. The locations could be very remote, where it may not possible to have this execution of transmission line or to have the centralized grid system. The location could be very remote and the community is very less. If you have to construct like 500 or 200 kilometers of line, and there are few houses only, so it is not economically feasible to have the centralized grid network. So the reason could be because of the remoteness, or it could be because of the cost, that the centralized grid system is practically not feasible. But still, you see, where are human being, electricity need is always there. So as I give example, for example, SADC country in African continents, significant population, around 20%, just have the access to the grid. So African continent, there are so many countries where the electricity situation is really poor. So any power system which can generate supply power to those locations, we call by several names like the remote, decentralized, standalone, autonomous, isolated power systems. In fact, long back I did my PhD around this topic, dealing mainly with the wind diesel hybrid power system. Okay. Because if you see it, like say 20 years earlier, PV was not much. PV was very costly. Now, of course, things changing. So here, if you talk about those remote locations when renewable energy was not so popular, so the most common way to supply electricity to those locations was mainly through the diesel generators. Okay. So if you see the advantages and disadvantages, advantage of the diesel generator is that it is very well proven technology. You have the diesel generator, you have the diesel supply, and the diesel generator will work well if the diesel generator is well maintained. Okay. So there are not much problems as far as the electricity generation is there from the diesel generator. However, you see that there are so many issues with the diesel generator. First of all, the cost of electricity produced is very high. This is because of the cost of fuel itself, which is very costly. Then the transportation cost for the fuel. Even think of the remote locations, it could be in the remote island countries or very remote locations. So how the diesel will be transported, even when we have to do the maintenance for the diesel generator. Okay. So sometimes specialized maintenance is required for diesel generators, so that may need the technician or engineers traveling from the cities to the remote areas. So overall, if you add the cost of electricity produced from the diesel generator becomes significantly higher. Now, interestingly, the book I mentioned, the design of wind diesel hybrid power system, it very nicely mentioned this point that when we have the isolated power system, in that case the peak demand could be significantly higher. The book states that it could be 5 times of the average load. So if the peak demand is high and you really want to meet the peak demand, when you are designing the system, you will design the system taking care for the peak demand, also taking care for the future expansion. So in that case, the size of diesel generator would be significantly large. Okay. You have to take care for, because the system is isolated. So even peak demand is there, it occurs for very short duration of time. You have to take care for the peak demand. You take care for the some future expansion. So in that case, the system you design, you can say somehow keeping the sort of backup. So system is, you can say, little bit oversized. So that will produce the electricity which will be further very costly. Okay. So there are these some concern issues that the cost of electricity produced from the diesel generator is very costly, and some other issue what we discussed yesterday as well, that diesel generator very noisy, it produced lot of noise. Okay. And then other issue, it produces the noise, and then other issue, noise, pollution. So these are of course concern. Okay, like when we have some specific services, okay, some specific services we are dealing, like for example noise example I am giving. For example, where you see that some priority building are there, like say where TV transmission is taking place. In that case, for example, if you have electrical tube lights, so you have this choke. The choke will also produce the humming noise. So they will make provision that all the electrical chokes will be placed outside the room. Okay. So depending upon what kind of application you are designing, so noise could be one of the concern. Same way when we talk about the air conditioner can make some significant noise. So when we see the split AC, part of the AC will be placed outside. So when we are designing the system for what application, it becomes very essential that what are some specific customer needs. So we have to take care for those issues as well. So here cost is one of the major concern, because we will expect that the communities living in the remote areas, poor community, so very difficult for them to afford. So whatever the power system we design, it should not be very costly. So here, if along with the diesel, if whatever we can see that what are the natural resources available in terms of wind, sunshine, biomass, micro hydro, whatever different natural resources available, so it should be exploited for the electricity generation. So when we can add the along with diesel generator, if you can add the other types of generation, wind, PV, micro hydro, whatever available, depending upon the availability of the sites. So this system we call it the hybrid power system. Generally a hybrid will have more than 2 types of sources, it can have more as well. So what will be the advantage of this hybrid power system? Obviously it will reduce the cost, then whatever the system sizing you have got, okay, if you have only diesel size will be very big, okay, so its fixed cost and its running cost, it will be very high. So when we add the other resources, so the size of the diesel will reduce, because when we have the large size generator, but its loads keeps on changing. Sometimes the load is very less, maybe say 50%, okay, and then you are running the big size generator. So even its operation will not be an economical one. Even the technical constraint that means that generator operation, you should have minimum load, also in the coming slides, that for the stability purpose you should have minimum load available on the generator. So basically with the hybrid power system, it will reduce the generator rating, it can reduce the battery sizing, it can reduce the pollution, and moreover when we have the diesel generator, in remote areas, so just very basic electricity is provided, like you see electricity for 2 hours in a day, 3 hours in a day, and just to supply some very basic needs, 2 lighting points, maybe 1 fan, something like that, very basic. But we expect that community should also can have some improved life, so at least they can use some other essential equipment as well. But that will depend upon if we can expand the size of the hybrid power systems microgrid. So when we have the other renewable sources integrated along with the diesel, so the size of the hybrid power system can be increased, and the community can be supplied not only just the basic minimum power, but they can be supplied little bit more power, and they can be supplied power for a good number of hours depending upon how big system we design. So maybe if it can be supplied continuous power, it will be really great. So you can see that in the remote areas, so this hybrid technology is really the great technology. So like say you will see that what should be the solution in the remote areas. So any system you design based on the hybrid power system, which will be really great. So and of course, like at least when we have this remote system, we want to ensure that electricity is there. We want to keep some kind of backup as well. So when we have any isolated system, in that the backup system is very important. So backup system could be mainly through the diesel generator, like we talk about, like in the city itself, we are sitting in the city. So what kind of backup we have? Diesel generator. Not only just like say 1 or 2, you will find several diesel generators. Okay. So the diesel generator is generally there. So this hybrid power system will be operated diesel in parallel with the other renewable energy sources, wind, micro hydro, bio, any type of renewable energy sources which are available that can be connected along with the diesel generator, that will form your local grid, what you call this isolated microgrid. So here with the microgrid, obviously how the cost will reduce, because whatever the renewable sources are there, as I mentioned, like the wind, solar, no fuel consumption or free. Even micro hydro, you can also consider that also to be almost free to some extent. So basically generally you can say no fuel consumption with the micro renewable power generation, and then of course it will increase the system sizing, and it can help the continuity of the supply along with the diesel. So this way microgrids could be a appropriate solution. Okay, but even we are designing the isolated microgrid system. If it is grid connected, so in case of grid connected system, there is very nice backup from the grid supply. Okay, so we are not too much worried about the backup, but in the remote areas, backup system is really very important. As we see that renewable energy sources like wind, PV are highly fluctuating, so it will affect quality of supply, and as I explained yesterday, whatever power system we have, grid connected system, isolated system, we have to maintain the active power generation between the active power generation and active power consumption, balance between the generation and demand, both real and reactive in the real time system. So, in the real time system, we have to maintain the active and reactive power balance within the specified limits. Okay. If this balance is not there, that will affect the quality of supply in terms of voltage and frequency deviation. Here in the isolated power system, managing the voltage and frequency within the limits becomes more challenging task, because here system is significantly dependent upon the renewable energy sources, so which are highly fluctuating. Okay. So, the control aspects in case of renewable power systems becomes more challenging task. Okay. So, in power system, as I mentioned yesterday, power system control, the frequency deviation are mainly dependent upon the real power mismatch between the generation and demand, whereas voltage mismatch is mainly dependent upon the reactive power unbalance in the system. So, how we can achieve the active power balance? Either by controlling the generation. On the generation side, you match the generation corresponding to load. Okay. So, we can call it the automatic generation control, AGC. You are controlling the generation depending upon the load from the generation side. Or another option could be that whatever generation is available, you control the load accordingly. You make the control from the load side. It's called as the load frequency control. So, as the generation, whatever generation we are making, then load accordingly we control. If the generation is limited, load is more, we have to do some priority scheduling of the load. If needed, we may need to do the load shedding as well. Okay. So, we change the load according to generation. So, basically we manage the active power balance between the generation and demand. Same way, we have to maintain the reactive power balance between the generation and the demand. So, here we will talk more about that. You have to see in power system what elements, what devices consume the reactive power, what devices, what elements produce the reactive power, and then you accordingly you provide the balance. For example, as we know, induction motor will require the reactive power. That reactive power, inductive reactive power, you compensate by providing the capacitor banks. Okay. So, basic idea is that we provide the reactive power support, maintain the reactive power balance to keep the voltage within the limits. Okay. So, here we can have a microgrid. As I said, nowadays we call it more popularly microgrid. Little bit previously you can call it like the hybrid power system, whether it is grid connected or isolated. So, here you can have the different sources of power generation. Okay. If it is grid connected microgrid, maybe diesel may or may not be there. Okay. But if you have isolated, then generally diesel generator will be there as the backup. So, what renewable sources you can have depending upon the availability of the natural resources like wind, PV, bio, micro hydro, etc. So, you can have these renewable energy sources. Then when we have these renewable energy sources, then we also need the converters, power electronic converters. Obviously, load will be there, and to manage the active power generation and active power consumption, we have the energy storage system. Then to maintain the reactive power balance, we can have the reactive power support elements in terms of capacitor banks. Also, we can have a little bit advanced reactive power compensating device like the SVC, static var compensator. Okay. Then, of course, you can have other, in modern microgrid, you can have some other, systems like these, some control and management communication systems, as we are trying to standardize, develop, appropriate protocol standards. So, then we are talking about some other issues like the islanding, etc., protections. So, depending upon the size of microgrid, you can have several features. Okay. So, how many these features you will have on the microgrid? It will also depend upon the size of the hybrid power system. For example, I give you an example. If you have got very small size of diesel generator, just very small size. So, for that you will have just some basic functions for the control. But if you have got the really very big size of diesel generator, then you will have more sophisticated controls, because whatever the additional cost incurred on the large size, you can justify that cost. With the small size, if you make the control system very costly, so it doesn't justify. So, these different components, you can see this reference paper, so very nicely documented. So, when we are talking about the similar way, little bit the different components what we are producing, microgrid, hybrid power system, we have, for example, diesel generator, wind systems. There can be other types of generators as well. So here the diesel generator, what type of the electrical generator it will have? So generally it will have the synchronous generator, because the speed of the generator is fixed. It is not variable like the wind speed. Okay. So whenever we have this fixed speed prime mover, we use the synchronous generator. Then wind, what type of generator we can have? Like say if we use the induction generator, particularly in the remote areas, so the cost of this generator will be, cost of the system little bit reduced, say 5%, 10% overall cost will be reduced. Then you need to have appropriate control system. Then of course you have got the consumer's load. Then you have got some kind of reactive power support. If for example your generation is more than the demand, okay, so if your generation is more than the demand, then you may need to have some kind of dump load, because you have to match the real power generation with the demand. Okay. So excess reactive power, excess real power generation, how you consume to maintain the frequency balance. So you will have the kind of dump load. Dump, as the name indicates, is just like dumping, like wasting. But if you can have some useful means to utilize power, even if excess power is there, if you can find some useful means like space heating or some other application, so that will be great, rather than just like wasting the electricity in terms of like the heaters which do not you use. Maybe you can find some useful means, okay, but end objective is that you match. Okay. Then of course if there is shortage, then you will have some kind of storage system. Okay. So here you will see that we are matching the real power generation with the real power consumption in real time. Same way reactive power generation with respect of reactive power consumption. Actually, I am discussing these points, the book I mentioned, I will show the reference at the end, like the wind diesel hybrid power system. Okay. So some points you will find really very interesting, that when we have the wind diesel hybrid power system, even for example think of you have got the diesel generator. If the load keeps on increasing or decreasing, or if you have to, for example, little bit increase in the load, little bit decrease in the load. So whether you should have frequent on and off of the generator, okay, or you try to have little bit reduce the number of on and off of the generator. If you frequently make on and off the generator, it will cause unnecessary stress on the generator. Okay. If frequent switching on and off, so here you could have basically two operation. As the load is increasing, decreasing, accordingly you are trying to make the generator frequently on and off, or you have this like the continuous operation. Okay. So both will have some pros and cons. If you are having the continuous operation of the generator, your control architecture will be simple, system is little bit more reliable, but obviously it will have more fuel consumption. Okay. Then the other option, you have that intermittent option, where you have the, when you have this several time switch on and off the generator, so it can reduce the fuel consumption. but your control system will become little bit more complex. So basically you can have this like the continuous operation of the diesel generator or intermittent operation. Like some of the quality parameters we keep in mind, whether it is conventional power system or renewable power systems, what quality parameters we talk. Two important parameters we talk: the voltage stability, frequency stability, extremely important, these two parameters, voltage and frequency. Then some other quality parameters we talk in terms of like harmonics within the limits, power factor should be reasonably high. We talk about the balance, phase balancing, electromagnetic interference. So these are some of the quality parameters what we expect in the power system. Now let us little bit discuss about the choice of the generators. In principle, we can have like the three types of generator: synchronous generator, induction generator and DC generator. So DC generators nowadays are not used, because wherever we need the DC power, we can rectify AC power into DC rather than having the DC generator. Okay, so DC generator are now almost obsolete. So in these two options, synchronous generator and induction generator. So synchronous generator we will be using where we have these constant speed applications like the diesel generator. Okay. So as we have the synchronous generator, so in synchronous generator reactive power can be controlled through the field control of the synchronous generator, and of course this synchronous generator will require the synchronization. So it has to be synchronized. If there are, say, in the hybrid power system there are 2-3 generators, so all have to be synchronized for a sort of local grid. The synchronous generators are more costly than induction generator, and one more technical terms it talks that it says that synchronous generators are closely coupled device, that is they have low damping, may require additional damping to reduce the turbulence. Okay, these are some of the key aspects of the synchronous generator. Now let us talk about the induction generator. So this induction generator, and as you know, based on the induction machine you can have two types of the generator, one based on the squirrel cage induction machine, other is the slip ring or wound rotor. So the squirrel cage generator is very robust in construction, it requires very less maintenance. So in the remote areas the squirrel cage induction generator is very popular. Even in the small mini micro hydro, the induction generator are popular, and of course they are less costly as well. Okay. And it adds that they are loosely coupled and have the ability to absorb slight changes in the rotor speed while remaining connected to the grid. We also talked about this. Sorry, this first synchronous generators are closely coupled device. So they have the low damping and require additional damping to reduce the turbulence. Whereas the induction generator, they are loosely coupled device. They are more flexible, more robust in operation. They can absorb slight changes in the rotor speed. Synchronous generator, as we will see that you have to operate corresponding to synchronous generator. Induction generator, you have got some flexibility for their operation in the rotor speed while still remaining connected to the grid. So, role of power electronics in hybrid power system when we are talking about this PV integration as well. So, the power electronics role, as I mentioned yesterday as well, is extremely important, using AC DC AC converter for induction generator. The wind turbines can be allowed to operate at the variable speed. So, the operation becomes variable speed operation, and these power electronics converters can be used for improving the quality of power supply. They can reduce the harmonics and then they can improve the power quality. And when we are talking about this like AC DC AC converter, so the wind system operation could be variable, so that can improve the aerodynamic efficiency of the wind turbine. You can produce the more power, you can reduce the stress and it can offer some additional benefits like the noise from the wind turbine from the low wind speed can be reduced by reducing the speed of operation. So, there can be some advantage, significant advantage for the variable speed operation. Now, for example, when you have the diesel generator, you want to make the choice of the diesel generator. Okay, some of the features, what way you will classify, how you are going to select the diesel generator. So, diesel generator abbreviated as DG. DG we also use for the distributed generation as well. So, you have to be careful, how you are using the abbreviation. So, this diesel engine and DG set. DG set is your diesel engine and the synchronous generator. So, it will convert the diesel fuel into mechanical energy in the diesel engine, and then mechanical energy is converted into the electrical energy in the synchronous generator. So, how you can categorize or classify diesel generator based on several classifications like the type of fuel used in the diesel engine, what is the engine speed, form of aspiration, operating cycle. So, type of fuel can be like number 2 diesel oil, light oil, or you can have the crude oil, heavy oil. So, depending upon which type of fuel is available comparatively on what cost, which one performance is comparatively better. So, that you may consider when you selecting the appropriate type of diesel generator. So, choice of the fuel will depend upon the cost, availability of the fuel, CV stand for its calorific value, temperature conditions, specific engine features. Small diesel generators can use number 2 fuel. Diesel fuel accounts for 80% of the operation cost. Whatever you have this operation cost, so fuel cost is significant, around 80%. Aspiration, what is the aspiration? Engine can be naturally aspirated or turbocharged. So, in naturally aspirated, air is taken at the atmospheric pressure, whereas in the turbocharged, air fuel mix at higher than atmospheric pressure can increase the engine efficiency. Okay. So this is what we call it the aspiration, how this engine is, whether it is naturally aspirated at natural atmospheric pressure you take air, or it is turbocharged. Okay. So then talking about the operating cycle. Okay, little bit more mechanical side, but it is very important to know about these different features as well. So operating cycle, as you will see any engine, it can have 2 cycle or 2 stroke or 4 stroke. Okay, for example, the scooter we have got the 2 stroke, whereas the car we have got the 4 stroke. So what are these 4 strokes? Like the suction, compression, then expansion or useful, and then finally exhaust. So there are basically four cycle. So suction, like for example, if you are talking that air is sucked, then air will be compressed. Then when air is compressed, its temperature increases, then fuel injection will be there, ignition will be there. Okay. And then of course when the fuel is ignited, it will cause the pressure, it will cause the crankshaft to move in the backward direction. So like this expansion or like the useful stroke, and finally exhaust. If it is the four cycle, it will have like this suction, air is filled in the cylinder, then compression, then further expansion and exhaust. Okay. So four operation of the crankshaft. But if you got the 2 cycle operation, then suction and compression like in one, and then expansion in exhaust like in one. So you see that you can have the like the two cycle operation or the 4 cycle operation. If the generator is small, you can have 2 stroke, but the generator is large, you will have the 4 stroke. So 4 stroke engine performance is better. Okay. Then how you are cooling the generator? So if the generator is small, it can be naturally cooled, but if the generator is bigger size, it could be forced cooling, it could be forced air cooling based on the fans, or it could be cooled on liquid cooling. So appropriate mechanism for the cooling. What will be the speed of the engine? Large size engines will operate at the lower speed, generally around 900 RPM. Higher speed engines are common in medium speed, and this speed could be something 1200 and up to 3600 RPM. Okay. So lower speed is generally applicable for the large size engines. Now what sort of the governor control you have got for the engine speed? So this governor control very important, so which will basically regulate the frequency. Through the governor control, you can control the fuel input to the engine. Okay. So accordingly, whether you have this higher load on the generator or less load on the generator, accordingly you will vary the fuel input. So this governor will control the fuel input to the generator. So all type of generator, small size of generator can have this mechanical type of the governor, but the modern large size of generator will have the electronic type of governor. Then of course the large size generators generally operate in the droop mode, which allowed the speed and voltage of the generator to slightly change with the change of the load. Generally you will see that our power system have got the droop characteristics. Okay. So as the load on the power system will increase, the frequency will slightly go down. If the load is lower, frequency will go higher. If the load is nominal, frequency will be nominal. Now talking about the like this wind turbine sizing. So like when in the hybrid power system you have to decide the size of the, talking little bit design of the different components. Okay. So when we are talking about the what should be the size of the wind turbine, it says that in principle that wind turbine size should be greater than the maximum consumer load. What will be the maximum customer's load, plus you have got some system losses. So and if you got some kind of like the plus system losses, and of course like when you are selecting the wind turbine or any size of any equipment, one is that what is based on the design. Then of course you have to see what sizes are commercially available in the market. Okay. You have to select from those available. You cannot order like your own size based on the calculations. So you have to see what is available, and when you are making final decision, then cost consideration is very important. Which manufacturer, what size, the cost is also given the due consideration. Okay. Then talking about little bit about the dump loads, like where you have this excess power generation that you are going to dump. So purpose of dump load is to dissipate excess energy of the wind system. Okay. You are not going to that you are generating the electricity from the diesel and dumping it. Okay. So excess energy what you have from the renewables, okay, that you even after you have stored your batteries, still the power from the wind is more. Okay. Even you are not running the diesel generator, even the power is more than your load. So that additional renewable energy you have to dump, like from the wind or even from the photovoltaic. Okay. But obviously you are not going to do that you are also operating the diesel generator. Whatever excess is being generated, that you are dumping. Okay. So at least diesel generator simply you switch off. Okay. So the purpose of dump load is to dissipate excess renewable energy from the wind or PV, which cannot be stored, to preserve the stability of the frequency and the voltage. So this dump load sizing, so this dump load, what rating you will be selecting. For example, you have got the electric heater as the dump load. So what should be the rating? 5 kilowatt, 10 kilowatt, what rating you decide. So in principle, the dump load rating must be able to accommodate maximum input surplus power expected from the system. Okay. How much in worst case scenario? In worst case scenario, how much maximum surplus power you can have it? Okay. That you will be dumping. When you are designing something, you consider the worst case scenario. Okay. So, what it could be there, which requires the knowledge that you have got the customer load which is minimum at, you consider that what will be the minimum customer load. Okay. But at the same time, you consider that maximum power is being generated from the renewables. Okay. And diesel generator you are running with the minimum capacity. Okay. So, you consider the worst case scenario to design the dump load rating. Are you following? So, when you are designing, you consider the worst case scenario. And of course, as mentioned previously, that considerations should be given to make use of excess energy in the form of like the space heating, if you can make some useful way of dealing that rather than just wasting the excess energy. Okay. Then like some of the storage options depending upon the application, you can have the different storage options in terms of batteries, lead acid, nickel cadmium, the sodium sulfur, other type of mechanical storage system, flywheel, superconducting magnetic energy storage system. So, you can have various storage options. So, when you are talking about the batteries, so batteries will provide the storage, and they try to when there is shortage of the power, so they can do the backup. So, in recent time, lot of research going on the battery. We now starting talking on the electric vehicle. So, battery is extremely important. Now, which specific battery you are going to select? You have to give the consideration of several parameters. Like when you are selecting the battery, that you give the cost consideration, very important. How much will be the weight of the battery, particularly when you are talking about the electric vehicles. Okay. Then number of charges and discharges, operation it can have, efficiency of the battery, temperature performance, discharge rate, charging rates. So, several technical parameters you have to consider, and then of course cost to finally decide the selecting of the appropriate type of battery. Okay. So, here you can see little bit more classification. Again I give the reference. So, in this year, in this volume, it was kind of special issues, so you can find several interesting papers. So, here you can have a classification for these batteries, like electromechanical batteries. You have the options like the lead acid, lithium ion, this redox. So, there are so many batteries options available. Mechanical in terms of like flywheel, pumped hydro storage, compressed air. Then based on these capacitors, supercapacitors, superconducting magnetic energy storage. So, you can have several options available. If we see that for these different types of energies storage, how much capacity it has been installed. Okay. The slide may not be very recent, but like it will give you some idea that what is the largest size of this storage system what we talk. Obviously, it is the pumped hydro storage. Okay. So, in the conventional power system, in almost every country, they try to have few pumped hydro storage, because storage capacity is generally significantly high, could be 500 megawatt, 1 gigawatt. So, this size is really significantly higher when you are talking the conventional large power system. Okay. Then compressed energy storage in terms of batteries, you will see the the batteries installation, you see compare with respect to pumped hydro storage, so it is quite lower. Then of course you have to see what are your needs, requirements. So I think this was some special paper on the storage system. Okay. So it talks about some of the common characteristics for the different type of storage systems. Okay. So you have got, for example, ultra capacitors, lead acid batteries, and several other types of batteries. I am not reading all these things in detail, but this is self-explanatory. How much is the specific power production in terms of power, watt or kilowatt per kg. Okay. And then specific energy. So, like what you call the power density, energy density, or specific power, specific energy in terms of energy per unit of weight. Okay. Then life cycle. So you have to give consider what will be the how many charges and discharges it can have. So that will decide the life of the batteries, and then the discharge rate and the efficiency for the storage system. So you give the consideration for several number of technical parameters to see that for a particular application which type of storage system could be most suitable option. Okay. This may be little bit old. When you are referring, please try to have the latest information. This the battery technology expanding very fast, so things keeps on changing very promptly. So you give consideration for this density, cost, cycles, charging time, power. So all these technical considerations are given. So these above values, it says that approximately battery technology is rapidly changing, and there are many different types with each categories. So for stationary application, like lead acid is quite good, and for electric cars, maybe lithium ion battery can be appeared to be the good options. But this again you have to consider the various options. Talking about the, like say when you are managing the energy management. Okay, you are managing the real power generation with respect of real power consumption. As we talked about the AGC, automatic generation control, or we talked about the load frequency control. So you are managing the demand. So how you are managing the load? You can manage the load what we call is from the demand side. Demand side management, or abbreviated term DSM, demand side management. Okay. So, problem of wind power variability can be tackled by the load or demand side management rather than to match the generation to the customer load. Load management involves to vary the load to match the power available. You can have priority switching loading as well. So, you need to consider the load management. Now, little bit mathematics, talking about, if you have to design the generator, very simple calculations. Rating of the generators, how you decide the size of the diesel generator, some technical calculations. So, how much is the active power demand? So, for example, you can have this active power of the synchronous generator decided by this power consumed by the load, dump load, and then wind. So, wind power will also supply the real power, so that will be subtracted. Even if you have got say photovoltaic, so you can subtract that. So, depending upon what are the different renewable power generation, so accordingly you have the suitable equation for the real power. Same way reactive power. Reactive power, again you will see that in the hybrid power system, which device supply the reactive power, which device consume the reactive power. Okay. So, like the reactive power, if you have this inductive load, so inductive load will consume the reactive power. For example, induction motor loads. Dump load based on the some inductive load, you can have this, and then the wind power. Okay, wind power, whether it will be this positive or negative, it will depend upon the type of generator. If you have the synchronous generator, it can generate the reactive power, but induction generator, it will consume the reactive power. We will talk more about that. Okay. So, this reactive power from the wind depending upon the type of the generator technology. Okay. So, here it says that assuming that it is induction generator, that is why it is positive. Had it been synchronous generator, then you consider is the negative. So, assuming that dump load have thyristor control, if the dump load is having some thyristor control, it will switch on and off at zero crashing of the voltage. So, reactive power demand for the dump load will be 0. So, what sort of system you are designing, you decide. Then of course, you have the different factors you consider, how much input you have got, how much knowledge you have got, that wind turbine has the converters, what firing angle they operate. Accordingly, the reactive power for the wind system you can determine, as you have this right angle triangle, real power of the wind is known, then tan phi, Q is equal to tan phi, you can decide the reactive power of the wind turbine. And what is the power factor of the system? Say, for example, 0.8, maximum reactive demand of the load is a QL is PL 10.5. Okay. Accordingly, once you have determined the real power of the generator, reactive power of the generator, then as you know, P square plus Q square under the root, we can get the apparent power as how much will be the the kVA or MVA rating of the generator. So all these simple calculations we go as much data as we have to get the some sort of the design. So basically I am not going into too much of detail, but you consider some simple cases with these different options whether wind power generation is more than the wind power generation capacity is more than the load capacity, or it is lower than the load capacity. Accordingly, you consider the different options for calculation for the synchronization. When you are deciding the sizing, particularly in the remote areas, so you consider the rating. So this way, basically, I explained the different devices like the dump load. Just you don't say that okay, this dump load, let me have any dump load, because when you are doing the technical design, then we give the consideration for the appropriate technical design. Okay. Now here actually I did my PhD in the similar area. So interestingly, for example, we have the hybrid power system. Okay. Now we as the electrical engineer, we see what type of generators we have got. Okay. What are the different varieties of the electrical system equipment we have got. So basically, when we are talking about the power system control, we are talking about the power system control, load frequency control. We have the significant literature available talking about the load frequency control, AGC. But when you are talking about the reactive power control, okay, because one thing is that in general we used to have the thinking that active power is the realistic power which you are using. We will think that reactive power, imaginary power is not useful. Okay. So we give the very less weightage to the reactive power, and the reactive power modeling, it was not significantly available in the literature. If you find the books, so not much, particularly when you are talking about this along with this renewable power generation. So I did maybe around now it's 22 years. Okay. So here again another interesting point, you will see that when we are dealing this mathematical modeling, as you do the course like the circuit analysis, first year, second year level, we talk about the KVL and KCL. Okay. But when we move to this electrical engineering in the power course, okay, then we talk about the power flow equations. We deal with the power flow equations. Okay. So this modeling, what we developed based on the not on the KVL, KCL, but based on the power flow equations. So here, interestingly, I will go through quickly just to give you a little bit flavor of this very important aspect, that the power flow equations, power based equations for the mathematical modeling for the induction generator particularly for the synchronous generator, you can find lot of literature available, but on induction generator, you don't find that much literature available talking about the modeling, particularly for the reactive power control in hybrid power system. So here, as I mentioned that when we are using the induction generator, particularly the squirrel cage induction generator, so it offers several advantages in hybrid power system: reduction of the cost of the generator, overall cost of the system. The generator is very robust. The generator has very less maintenance, and there are several features. So basically, in the isolated power system, the self-excited induction generator is a very appropriate choice. I wrote a review paper long back, you can see around 2005. So was very popular at that time. I think it has achieved some good citation, maybe 700 or something like that. So basically, some of the issues with the induction generator, it will require the reactive power support for its operation. It will need the reactive power for its operation. Now, induction generator, when you are having in the isolated mode, it is not connected to the grid, then reactive power you will supply externally by means of the capacitor banks. Okay. But if this induction generator is connected to the grid, then you can get the reactive power either from the grid or you connect the capacitor bank along with the generator. If you are drawing from the grid, it will stress the grid. So there are different options, but the induction generator needs the reactive power for its operation. So in the when I studied, so mainly you will find that induction generator modeling in previously several papers, it was based on the impedance and admittance modeling. Like the equation one, you say V is equal to IR, okay, V is equal to IZ, or another is equal to current is equal to I is equal to V into Y. Okay. So in this we specifically develop this based on the power equations. So I will not go into very much detail, but you will have like the induction machine, induction generator. Okay, you can see the induction machine circuit you can present in the simplified equivalent circuit, series circuit, parallel circuit, and then you have this equations what we see. Okay, so I am not going into very much detail. Then we published like one paper talking about this mathematical modeling for the induction generator for reactive power control. Even slides we will provide, but if you need, you can ask from me some of the research papers as well. Okay, if any of these papers I am discussing, if you need it, I will be happy to share that additional research papers. Okay, so in this like the very detailed modeling it was developed. I took long time. At that time I did my PhD part time. In fact, I did my PhD from IIT Delhi with Professor T.S. Bhatti, Center for Energy Studies long back. So it is now getting more than 20 years. Okay, and then basically all this very complex mathematical modeling you will see is being developed here. So the reactive power required by the induction generator. Why this minus sign is coming? Because it will need the reactive power spot. Okay. So, here basically all this detail modeling I am not discussing, but you can see that this modeling quite complex, quite detailed. Even you can see how the reactive power of the induction generator will be varying, because induction machine at what slip, if the slip is changing, so its reactive power requirement will be changing. So, we develop this concept what you call as the constant speed or variable speed, how the reactive power will change. Okay. So, we develop this detailed mathematical modeling. Then when you are dealing in the hybrid power systems, then you will have other generator like the synchronous generator attached to the diesel generator. So, you have to have the model for the synchronous generator, particularly what study you are doing for the load frequency or mainly reactive power control. So, you write the appropriate model, deal with the appropriate model for the synchronous generator. I am not going into the too much of detail because of the time constraint, but at least you can get some kind of feeling. Then like this flux linkage equations what we deal. Then if you got the reactive power spot, capacitor banks or static VAR compensator, you have these appropriate equations, that reactive power spot provided by the static VAR compensator, you have that appropriate equations. So, all these detailed mathematical modeling you have for the individual components. Then you have again in your hybrid power systems. Hybrid power system, you want to have the reactive power balance, which devices are supplying the reactive power, which devices consume the reactive power. So, you try to establish the appropriate balance. For example, here synchronous generator supplies the reactive power, SPC supplies the reactive power, load generally consume the reactive power. Induction generator could be based on the wind or small hydro, consume the reactive power. If you have got the photovoltaic or some other generator, you suitably modify these equations. Okay. Then you deal with the analysis, as we call it, like small signal analysis, small scale signal stability analysis. Okay. So, you deal with the small scale changes, and you go into this mathematical equations. I am not going into too much of details. Then of course, you have got the load, what kind of load you have got. You have to do the load modeling, appropriate type of load you have to select, you have to do the load modeling. Then finally, in the system, you have the for the small deviation, you place this equation. Okay. Equations. So, basically, as you are doing the power equations, as we mentioned, load frequency control. Okay. As you had in the power system, what you have got, the turbine, then generator in the feed forward loop, then the feedback loop, you are taking the signal from the output side, that signal you are feeding to the input side. So, this forms you the everything you put in the each block you place in terms of the transfer function. Same way here we are trying to place that our reactive power model for these power equations. So this you develop the appropriate model based on this Laplace transformer differential equations. So basically you are like say overall model system. I will little bit mention, for example, here you have got your reactive power support device, static var compensator. Then you have got here what you call that your synchronous generator. All these mathematical equations we developed. So this synchronous generator, with this synchronous generator, what type of excitation system you are considering? You can find in the literature IEEE systems that what type of excitation system you are selecting. Accordingly, you have your this excitation system associated with the synchronous generator. Okay, so this part your excitation system, this part you are seeing as your synchronous generator, and then of course like here you are seeing this like overall balance. Here you have this load, then whatever you have got this SVC, that SVC signal is coming here. All this power you are trying to make balance here. You can see that the small deviation in the reactive power generated by the synchronous generator, then reactive power, small deviation in the reactive power of the static var compensator. What you have, the reactive power consumption by the induction generator, that's why it's coming with the minus sign, and the reactive power consumption by the load. So how much is the small scale deviation in the reactive power? Okay, so you develop the appropriate model, use any techniques, can develop this in the MATLAB Simulink, or you can have appropriate program how you develop. So this was the case when you consider this like the constant speed, when you have the like this, when you consider the effect of variable sleep or speed. So in that case you have this additional quantities to show the effect of variation of this wind speed, So like here you can see that what you see for this induction generator in this constant speed, but in the another slide you will see that to consider the effect of variation of the wind speed, accordingly the slip of the induction generator will change and how the reactive power change will be there. Okay. And then of course you analyze, get the results, do the simulation for the small deviation, for this voltage and so many parameters. I am not going into the detail of that, but I will just refer like some of the some key publications, if someone is doing the research in this similar area. So based on the research we did it for PhD, then some additional research. So we published a book, Small Scale Analysis for Isolated Hybrid Power System, mainly dealing with the reactive power control, but little bit added for the frequency control. Frequency control you can find lot of literature, but reactive power you'll see this sort of modeling. You don't find that much frequently. Then some papers I mentioned, one this paper, then another paper, very detailed paper published in IEEE transaction on industrial electronics, automatic reactive power control for isolated wind diesel hybrid power system. And sorry, this book is already there, same book. Then this book I was mentioning, the wind diesel hybrid power system, it is quite old, but you may see that now you can have, this is not only the book, you can have some others book as well, like little bit some of the points I mentioned. So you can find some book dealing with some kind of design, so which can form as some good reference. Then as I mentioned, in this electric power component system, there are sort of special issue now, although it is little bit old, but you can see the microgrid architecture, controls, protection and demonstration. So this way we are just end of this session. End of this session. It took little bit longer, but I wanted to go a little bit more pace with this session. So we will just stop for this session. Maybe quickly, if anyone has, please, any questions from this physical or online participants, please feel free if you have any quick questions. We have little bit time, so any questions, please. Anyone doing the research closer to these areas? If no question, then we will probably take short break, and then maybe someone talking. Yeah, question. Yes, please.
Yes, sir.
Yeah, speak, please.
Yes, sir. Myself, B, sir. I just want to know from you that is there any potential? What is the potential of research in the automatic generation control of an isolated system of renewable energy sources?
Yeah, so it's very good question. In fact, the isolated power system, okay. Still, as I mentioned, still there are several locations worldwide where there is no grid supply, and particularly we are talking about this optimization, developing the appropriate standards, and you'll see that the frequency control is one of the key aspects of the power system control, particularly in the isolated system, because here both the generation and load are changing. Wind speed is varying, all these like input conditions are significantly varying, load is also changing. So making the balance with the active power generation and demand, managing the frequency control, it becomes quite challenging task. And when of course the technology is changing, the battery storage technology is changing, storage system is changing, we are getting the different power electronic converters. So as I mentioned in the yesterday lecture as well, that you'll see that the research being conducted in electrical power systems, most of the research revolving around the microgrid. It could be isolated, it could be connected with the grid. So in recent time, this is really one of the very hot topic.
But in the isolated area, if we are going for the renewable energy sources to supply the load in the isolated areas, then the supply of the reactive power demand will be quite expensive. We can say feature of that unit.
Yes, so that's very important. In fact, uh, the point what I explained, because when we are doing, say, for the like little bit from the academic perspective, then we go more scientifically, more detailed analysis. Okay,
Right.
and of course, depending upon how big is your system. If small system, then we don't go into too much of detail. As I give you example, if you have, like, for example, small 5 kilowatt diesel generator, what sort of control it will have, or one generator you consider, like, say, 1 megawatt capacity. So how much control architecture will be there? So it will depend proportionately. If it is a bigger system, the complexity will increase. We will go more careful in design of that, because it involves significant costs. So you go more deeper into that analysis, particularly if your isolated system is quite bigger. Sometimes you think that it is a kind of theoretical questions. Let me share little bit my practical experience. I previously worked in the Fiji Island.
Right.
So Fiji Island, small island country, having the very small island country, population less than 1 million. Okay, very small country, population less than 1 million. So there are 2 or 3 main islands, but if you see small islands, there are too many. So main island, what we call, have basically the electricity supply. You can call it the grid supply. Okay. So in that, at that time, mainly it used to be the supply, but you'll see that in that significant power generation from the diesel generator. Okay, small country. Now I think not very big, maybe around, say, 400 megawatt. 400 megawatt will be the total installed capacity. Very small, because the population is very less. So the diesel capacity is significantly higher. I have some slide, but I can show you. Diesel generator capacity will be significantly higher, maybe, say, around 40%. So out of 400 megawatt, the 40%, so around 100 or 150 megawatt diesel generator. Okay, so which is significant. You will see the diesel generator size, like in the range, like, say, 10 megawatt, 20 megawatt. Okay, so which consume significant fuel, significant cost. So in that situation, you really need to consider all these, detailed analysis, detailed calculations, even reactive power support, frequency control, what we mentioned. So I hope you are following my point, please.
Yes, sir.
Right? So there could be some specific cases where the system sizing could be really very big. Although the cost, talking about the microgrid small size, but yesterday I said that we are not just focused only microgrid, but renewable power integration as well. And renewable power integration in terms of like this PV farm, wind farm, to have this more and more renewable integration. So thank you very much for very interesting questions. Yes, please continue.
Yes, is there any example in the world where there is a DC microgrid system only? Hybrid is there. There are many applications, many arrangements are there with hybrid microgrid. But
yes.
Is there any example in the world with DC microgrid only? Pure DC?
Some of the example I showed you yesterday, I don't recall exactly, but maybe probably we can try to search and find out. I can let you know if I have a relook on the literature.
Yes, hybrid, there are many examples are there for hybrid, But for
Yes.
small loads, there are any DC microgrid, then but the cost involved in that.
Yeah, so maybe I'm not sure. Maybe some of the laboratories, small or
Yes, that.
demonstration
Yes.
purpose, they
Yes.
might have
Yes,
developed.
that is. Yes,
Yes,
that
yes,
is.
yes, yes.
Yes. Thank you so much.
Thank you very much. So now we are going to discuss energy management system of microgrid system. How we are going to manage the energy in the microgrid system. Okay, so I will talk little bit about the general introduction about the microgrid, how we are going to manage the energy from the generation side, how we manage the energy from load side. This energy management system could be a centralized system, or it could be a decentralized system. And then how we manage from the load side, the uh, we can control this energy from the load side. We can prioritize the load if needed. We may need to do the load setting. Uh, so I will speak very briefly about this some theoretical aspect. Then I will discuss briefly one research paper written by my past PhD student, like say how we do the economical optimal load management of microgrid system using energy storage system. So I'll just try to briefly discuss, as we will have little bit time constraint, so I will try to be little bit short, but I will provide these the full papers. So if anyone is more interested, you can go into the detail. Okay, so some of the general things, like what is the basic function of energy management system. The function of energy management system is to optimally allocate different energy sources to the customers, along with the integrating sustainable power sources without compromising reliability, security, safety of the system. So basically, energy management system optimally allocate the optimum allocation of the different renewable energy sources, mainly using this sustainable power system, ensuring the reliability, security, and safety of the system. So in energy management system can monitor, supervise, optimize, control the customer's distribution, transmission, and uh, and generation facility. So this energy management system is we see that grid is evolving complex network with the integration of electric vehicle, renewable energy storage systems, and renewable energy sources, energy storage systems, and many more factors. So this energy management system becomes more complicated with this integration of these renewable energy sources, storage systems, electric vehicles. So it gets more complication. However, with these new tools, techniques coming up, like the IoT, Internet of Things, machine learning, AI techniques, so this energy management system is getting popularity and simultaneously helpful for the efficient functioning of the energy management systems in the network. So similar terms like in the past, you would have heard SCADA, supervisory control, and data acquisition systems. So all these things like build up from this previous approaches with advanced features. So some of the function what it can do, it can give you some clear idea about the energy cost involved, can optimize, monitor electrical parameters for reduction of cost, can plan for future planning based of the consumption patterns from the energy management system, can meter the energy consumption and collect the data, kind of this smart meter function, and can quantify opportunity to save the energy, where it can save the energy, and it can monitor the progress for saving of the energy. So basically overall quite intelligent platform, this energy management system, that what it can do. So it offers several advantages of energy management systems, offers a cost effective solution. Human intervention is minimum, so human these errors in data collections are minimal, and then it is easy to configure and maintain, and helps to identify inefficient electrical equipment, can deal with the maximum power demand analysis, facility of viewing the real-time electrical data and energy reports over intranet or internet, has the provision of the graphical display of the energy consumptions, and can alarm for some unexpected events as well. So some of the objectives of energy management systems can be in terms of that it can have a single or multiple objectives. When you want to optimize, you can have like the single objective or multiple objectives, which could be technical, economical, techno-economic, environmental, and socio-economical. Because now the research what we are conducting, initially we mostly focused on the technical, then we thought that technical is not sufficient, we should also give the consideration to economical aspects, and then consider environmental aspects, the social economical aspects. So all these little bit interdisciplinary area becomes extremely important when we are conducting research, to make it practical research, the research which could be adaptable by the society. So considering in addition to technical, economic, techno-economic, environmental, socio-economic, so all this becomes extremely important. In next presentation, I will show that one of my PhD student, how he expanded research considering these different aspects. So basically with the integration of these electric vehicles, renewable energy sources, without proper coordination, it can cause the system to deviate from the intended performance. Technical objective of the energy management system can include power quality, effective performance, degradation of the transformer and other equipments, cables, and its consideration will provide better performance of the system, better power quality, improve life expectancy, reduce maintenance and downtime. Economic objectives refer to the economic aspect, as we know that reducing the total operating cost of the energy, cost to the customers, profit, maximization, etc. So all these aspects related to the cost minimization, profit maximization. Environmental objective, as we know, will cover the greenhouse gas emissions minimization, where the different fossil fuel based generation, mainly utility or distributed generation, and renewable energy sources are scheduled to achieve a low carbon footprint. So basically, environmental aspect, our emphasis is to have this more and more power from the renewable and sustainable power generation, to have this minimum emission as possible. Socio-economic objectives are considered, where economic activity is shaped by social process, which includes various programs in which end users, aggregators, agents, network operators take active participation to achieve the best economic outcome. This, for example, I mentioned this social aspect. Any technology is there, okay. So how the society is maintaining. In the morning class, I explained you about the microgrid. Okay, so I give a practical example when I was in Fiji Island. So basically, their technology is there. Okay, that we have the hybrid power systems, microgrid power systems. The government can supply these microgrid systems to the remote communities. No major problem about that. Okay, but regular maintaining of this microgrid has to be done by the local community. If it is very much remote, okay, chances are very minimum that people from the city or town will go, and just will operate it. Okay, so basically, the community has to be trained how the community is going to operate the microgrid system. So it is not only just the technology, but how the normal operation of the microgrid system will be done, and on daily basis how these duties will be arranged, so that everyone has the responsibility to operate the microgrid system. Okay, not only then the question will come, then the community is using this microgrid system, so how the revenue will be collected. Okay, all these aspects are extremely important, more than the technical aspect. If there is no proper coordination, no proper understanding how this microgrid is going to be operated, how these regular basis duties will be assigned, how it will be operated and maintained. So if that is not done in Fiji Island. I'm sharing the example that after few years, the microgrid system could be unfunctional. It will not because of this technical reason, but more of because of this like this social reasons, that if there is no proper care, no proper schedule, no proper arrangement, then how this microgrid will be operated and maintained. So these sort of factors becomes extremely important rather than technical, that how this microgrid will have the day-to-day operation, its fuel management, little bit maintenance, general maintenance. So all these things have to done by the local community. If there is something which requires highly specialized job maintenance, then of course it can be arranged at some specific period of time. But regular operation and maintenance has to be done by the community, and community has to be properly trained. If that is not the case, then the microgrid system can unfunctional after short duration of operation. So these sort of aspects are extremely important, and due weightage, proper documentation has to be done, how this community will be trained, how they will operate, even some logbook, how it will be operated and maintained. Even when we are operating any electrical equipment, could be transformer, generator, we always keep the logbook to have the regular readings. Okay, maybe hourly basis. Even sometimes someone miss for 1 hour, at least in 2 hours it will be taken. So this regular operation and maintenance, proper procedure, it is extremely important. Okay. So so all these things, like we are more focused about the technical aspect. You will see that in some other areas or some related to some other journals will be there, which will consider technical plus economical plus social aspects. So all these aspects are very, very important, for this final consideration as a product. So the benefit obtained from the social welfare based program is shared among all the players, including the end users. Like if you have any equipment, any device, okay, how nicely designed, at the end, if community does not accept it by heart, it can may not be very successful. Okay, for example, some device or something like, for example, solar cooker or solar water heating. Okay, so basically little bit effort is required. For example, when you have to cook it, you have to place in the sun. Okay, little bit inconvenient, you have to wait for some time, but sometimes people are impatient and say, no, this will not work. Right? So basically the practical and social aspect is very important. Even the solar water heating system, like if your bucket of water you keep in the sun, maybe little bit it can work, but sometimes people say no, very difficult, we don't We will be busy on mobile, we cannot do this thing. So, what I mean, that if society, doesn't accept, does not tune, if no proper encouragement, no proper training is there, and then it may not work well. So, whatever technology is there, we have to motivate, we have to encourage people so that they can really get benefited from this technology. And then, as I mentioned, that energy management system, it can be characterized, it could be centralized or it could be decentralized. Like how we are managing electricity in the grid, in the conventional power system. We used to call this like the national control center. Okay, that energy throughout the nation, it will be controlled in the center. Then we call it like, say, few regional control centers. So this way, like, you have the centralized control, then decentralized control. Okay, so there are different steps involved. So it is characterized by the central controller with obviously high performance computing unit and a dedicated secure communication network to manage the utilization of energy. How the distribution of the energy will be there, how this energy management will be there. So this centralized control provides optimal global performance, and it has fair share of some demerits as well. All the information is gathered, handled at one place. The computational burden increases, especially if large number of assets are to be controlled. Okay, thereby making this control structure little bit less effective for the real-time communication requirement, because all this huge amount of data has to be processed at one centralized process. Of course, we are putting our best efforts, secured connections and high performance computing. Still, because of the huge volume of the data, huge information to be processed, so it can have delay, it can have less effective. And if this imagine centralized control system fails, so it can be a major issue. So then we see, particularly in respect of this microgrid, we talk about the decentralized approach. So in this centralized approach architecture, it is characterized by distributed processing system, with each node having autonomous control capability and peer-to-peer communication with the other nodes. So it will overcome some of the limitations of the centralized architecture by enhancing the expandability, allowing greater flexibility of operation and avoiding like the single point failure. So some of the issues we see in the centralized one, so few can be avoided, and depending on the communication network, it can be fully independent, partially independent, or entirely dependent. Okay, so this is there. Then you will find like on energy management system, you will find many good reference, and you can have a lot of theoretical aspects. I will share at the end few references. So rather than going too much just discussion of the theoretical, you can read any review paper or nice paper. I'll just briefly share like one of the approach is in fact the research conducted by one of my PhD student, this Steve Madiba, so who did the economic load management control of microgrid system, like when you want to have this energy management or the load management of microgrid systems. You can have any approach managing the generation through the energy storage systems or through the load management. So basically in this paper, load management control application for an economic load shedding problem. So initially you may have the situation to have this load shedding. So how by managing the generation, even the storage system, how you can avoid this problem of the load shedding, and you can optimize the process, have the economical operation as well. So here the control scheme is based on the coordination for the diesel generator combined with standalone like this microgrid that contains renewable energy resources like the wind, photovoltaic systems, to biomass generation system and energy storage system. The control model minimize the diesel generator units fuel cost, because how we are going to have the optimal operation. Obviously one objective would be to have the minimum operation of the diesel generator to reduce the cost. Okay, so it is like one of the main objective into the microgrid. And in this microgrid is basically could have this a plant, for example any industry, sugar industry. So the waste coming from the sugar, so biomass which can be used for the electricity generation. So there could be any existing system, or you can design any system, the requirement that you want to manage the energy. So this optimal control scheme has been executed to minimize the diesel generator operating costs, maximize the energy from the renewable energy resources, and finally increase the, like say, microgrid, if it is operated by independent power producers, profit during the load shedding operation. So this strategy develops an under frequency load shedding. So basically, as I mentioned, the load like this generation and demand for real power generation and demand, it has to match. But if load is more, frequency goes down. If frequency goes down beyond a limit, so otherwise system will get desynchronized. So then again you have to have proper scheme that if the frequency is dropping by this, then you have to shed the load, or it can lead to have the blackout situation. Okay, so basically develops a strategy for an under frequency load shedding scheme to control the microgrid based multi-objective optimality. Okay, so this paper, economic operation of load management control of microgrid system using energy storage system, published in the Journal of Energy Storage, Elsewhere journal. So quite nice impact factor, very recently. So in fact, the student had completed his PhD, then you see once PhD done, they will be little bit relaxed. Okay, supervisor has less control because student becomes decentralized. So then you encourage, sometimes you ask some other student join in the team, help and try to write the paper, right? So I asked another student to also get engaged, build bigger team. So finally managed to publish, and which is good for both from the researcher and of course for the faculty's member as well. So here basically you'll see that in the paper, I will share this paper to you. If you feel interested, you can go in more detail. So in the literature, you will see that when we are having these like optimal operation, in the literature, different factors, what different research papers, they are numbered here, like what sort of factor they considered in the research. Okay, so some research paper they will include only this aspect. So what would be your new contribution? So you can include 1 or 2 additional factors. Okay, just to say that this is something extra. So you'll see that the major aspects that dealt are renewable energy resources impact, optimal load shedding control, adaptive strategy for the under frequency load shedding, optimal load shedding control applied industries, and economic aspects analysis of the load shedding control. So basically some of the researchers just include like the single point, someone consider like the 2 points, but here in this paper the main author claimed that he has considered all points. I don't know how much he considered, but we always say that we are considering something more. So this is like the schematic diagram of the system of the microgrid that you can see that proposed under the optimal model based on the under frequency load shedding. So it comprises of like the wind system, photovoltaic systems, and the battery storage system. Then of course it has got the 2 biomass generation, and then of course we have the diesel generator. So this is a microgrid system. So just for little bit idea, okay, the sort of parameter what these are considered. So you have the diesel generator, the rating 1500 kilowatt, so 1.5 megawatts. So it's not very small system, significantly good. The diesel generator efficiency 0.8, fuel price, at least when we are doing research, we need the data. Okay, we keep on searching where you can find some good data. Okay, either from some research paper or you try to get appropriate data, though this becomes very important. So this then diesel generator parameters A, B, C. So what are these parameters? Like how much fuel consumption will be there in the diesel generator. Okay, so it will depend upon some of the parameters. For example, you have your car, how much fuel it will be consuming. Okay, you have to model it. Okay, maybe some of the factor you have to consider, like the speed, how much speed up and down. Okay, so this way you have to consider some factors like on which this fuel consumption will depend. Same way diesel generator, how much fuel consumption will be there, you have to model it a proper equation. Then talking about these batteries, battery capacity 20 kilowatt hour or 5 kilowatt for 20 ampere hours. maximum state of charge, minimum state of charge, maximum 95, minimum 45, charging efficiency, discharging efficiency, charging efficiency 95%, discharging 80%, accepted microgrid system efficiency, frequency 50 plus minus 1.5 hertz, voltage 1 plus minus 0.05 per unit, because in the distribution system we allow the voltage variation of the plus minus 5%. In distribution system, permissible voltage regulation, allowed permissible voltage regulation is 5%, right? In the transmission system, it can be up to 10%. Then we have the biomass generators, both 2000 kilowatt, both 2 megawatt. Okay. Then loads, first and second load, 250 kilowatt. It is basically the industry milling plant. Is the student was from the DRC Congo in the African continent. So he said that I have some plan or some industries there. Is the corn industry. So residue from the corn will be used for this like this for the biomass generator. So it's that, you know, how much corn residue coming, 40, what is the price that you have to consider, $40 per ton, how much will be the calorific value, efficiency of the system. We have the wind system, small wind turbine systems, 5 kilowatt, PV systems, maximum 100 kilowatt, efficiency of PV system 20%. The maximum load capacities, critical and non-critical loads, first and second, 1500 kilowatt, second load 100 kilowatt. Then it also considers in future in additional load to the existing PL3, so it considered for the future load as well. So 1500 kilowatt, significant future load is also considered. Now, when you are considering the system, any you know energy management system you are proposing, like you are providing the additional power generation, microgrid, so you have to calculate the cost as well, how much cost it will add. Okay, so for this, like the biomass plant, all these costs are calculated for this biomass generation system. I'm not going into the detail. Then you have this like standby diesel generator cost, solar PV system cost, wind turbine generation cost, some contingency. So this way you do the cost analysis. Now the result, I am not going into too much detail about the results, but just I wanted to give you little bit flavor that what is the outcome. So assessment of the saving for load shedding solutions based on the optimal energy management. Okay, so in these different 3 scenarios are considered. In first scenario, that the microgrid is operating with the initial full load capacity, diesel generator, and the second biomass are not used to compensate the power system. So there is basically no load shedding, and this is there. Then in this scenario 1, for example, it says that microgrid with operating with the first biomass system, assuming to the renewable energy source supplier system, a future load development has been connected. First solution applied is the connection of the 1.5 megawatt diesel generator into the microgrid system. So here we are running the full diesel generator capacity. Okay, so you are seeing that you are significantly using the diesel generator. Okay, so here you are seeing that cost of electricity when you are significantly using the diesel generator, it increases significantly. Okay, so like in the other options, microgrid operating with both biomass generator, you are using the both biomass generators, assuming to be the renewable energy sources with additional future connected load. So you are considering that you will run both these biomass generator, including even in the future that significant additional load will come. You are planning for the future system as well. So here with this scenario, you can see when you are using the biomass system, you can see that there will be significant reduction in the electricity cost, and you can see that whatever the initially you have been using the huge amount of diesel, but now you are means that diesel you can optimize. So basically, if you design the appropriate like say energy management system for a practical situation, okay, how we are going to do that, maybe avoid the load shedding, or how we are going to manage, even you can provide the additional renewable energy sources which can offer green solution. It can reduce the cost. It can avoid the problem of the load shedding. So I was very short in discussing. So here, like I just discussed, like one of the paper. This way you can find like one more research conducted. So here I also contributed. So I will share this research paper as well. So it talks about the optimal energy management of the small nanogrid, microgrid using the battery storage system. Okay, again you want to manage the energy. Okay, so it could be managed from the generation side. It could be managed even battery, through the battery as well. You are managing from the load side, demand side management. And then these are some of the papers talking about the journal paper, journal article talking about the kind of review article. So you can read it if you feel little bit more interested knowing the theoretical background about the topic. I know like one of these the colleague from BITS Plan in India, so they have done few PhD around this optimal energy management system. So this is like one of the another interesting topic. So I have been little bit brief in discussing the topic as we have to little bit cover more. So we just did the small discussion about the energy management system in the microgrid. Please, if you have any quick queries, questions related to this topic, any online student or any physical students, please, if you have any queries, questions, feel free to ask. Okay, if we don't have the question, then we'll wait for 2 minutes and then we will move to the next presentation.